I'd like to welcome everybody to this fantastic presentation on Red Planet Day and pass across to Becky, which we are delighted to have. Thank you.
Hi, thank you very much. So hopefully you can still see my first slide.
Yes, definitely.
Excellent. Okay. So thank you very much for inviting me here today to share with you a little bit about astrophysics discovery and how that's linked to technology development. So I am an astrophysicist. I'm a senior lecturer at the University of Portsmouth. I arrived here, joined during the pandemic. So I've been in Portsmouth for nearly 2 years now. Before that, I was a research scientist at Stanford University in California. In particular, it's a great pleasure to speak to you on Red Planet Day today. So Red Planet Day is so called because it was the first time that we had a successful mission that reached Mars and produced pictures back for us. So these were our first deep space photos that came back. So I'll show you some more deep space photos, not so many of Mars, but you'll see some more of those today. So the title of this talk is How Computing and Engineering Help to Lead the Way to the Stars Might Lead Us Back to the Red Planet, with a subtitle of a short history of the last 13.9 billion years. Quite a lot has happened in our 13.9 billion years, but I'll try to keep this relatively brief. I won't tell you about the whole history of the universe, but in the time that we have today, I wanted to give you what I think are some of the highlights of astrophysics discovery. And in so doing, I want to kind of show that the role cutting-edge technology has had within astrophysics discovery. Discovery has accelerated in the last 100 years. And at the end, the question for all of us will be, what will the next 100 years bring? So astrophysics is the oldest science, and it began with our first important technology development, our first optics, and that's the eye. So with the naked eye and with a very dark sight, you can see about 6,000 stars. You can see 5 planets. So we don't need much technology development to observe Mars. Actually, in Mars you can see, I mean, millions of years of evolution perhaps, but we don't need telescopes, we don't need binoculars, we can observe Mars. Unsurprisingly then, these planets that you see have been known about for tens of thousands of years. However, despite the kind of the remarkable flexibility and complexity of our natural lenses, they're limited by both their size and by exposure time. So we can't ask our eye to gather all light for a minute and then look at the result in the way that we can do with a camera. So the fainter a thing is, and the larger the light bucket that you would want to collect those photons. So until technology developed larger lenses, the rate of astronomical discovery was really very, very limited. And this was more or less all we could see. In the 17th century, we did discover how to make faraway objects appear larger and appear brighter. And we did this using glass lenses. So very soon after our first telescopes were invented, this enabled the discovery of 2 more planets. So Uranus and Neptune were discovered in 1781 and 1846. So the first type of telescope like this is called a refracting telescope. And in theory, we can just polish bigger and bigger lenses and see deeper and deeper into the universe. But in practice, a big lens needs a very long tube. And the tubes essentially just become too heavy to move and too heavy to keep stable. So the largest refracting telescope that we have is in Wisconsin in the USA. It's got a 1 meter lens, and it's 18 meters in length for that 1 meter lens. It weighs about 20 tons. So lenses were a wonderful invention, but they very quickly reached sizes that were essentially no longer practical for us to use. And basically, this had the effect again of slowing the rate of discovery. until the next technological breakthrough for astrophysics. And that, of course, was the mirror. So mirrors mean that now you can not only bend the light, but you can fold it. So telescopes with large apertures no longer need to be big, or they no longer need to be heavy. This means that telescopes can be more stable, and they're not so prone to things like toppling over or swaying in the wind and blurring your images. And an equally important development in electronics occurred for moving and tracking stars across the night sky. So this occurred in about the 20th century. And this meant that we could now take long exposures of objects. So being able to add together the light that we receive from an object over several minutes allows us to collect more photons, and we can see many fainter objects. These first photos were exposed on photographic plates. And a big problem that we had initially with photographic plates is their calibration. So the level of flux that you would see varied significantly across the photographic plate itself. And it caused very difficult problems with calibration. So these two breakthroughs enabled both the discovery of the remainder of our solar system, but also something else that was quite remarkable. And that's the first galaxies. So this is an image here of our nearest galaxy amongst a lot of stars. So this discovery is actually relatively recent. This only occurred in the 1920s. So for me, that's always been something that's quite remarkable, because up until essentially 3 generations ago, we believed that our galaxy, the Milky Way, so our collection of billions of stars that we call home, that was for us our entire universe. Now, only 3 generations later, we're seeing images of some of the first galaxies that have ever formed in our entire universe more than 13 billion years ago. So that's an incredible rate of change. So as we develop better mirror and camera technology, our astrophysical horizons have essentially expanded exponentially. So we've gone from this picture to pictures like this. So this is actually Edwin Hubble observing in what they used to call the astronomer cage, where you would sit at the telescope and look through the lenses. And this is roughly what the sky would have looked like at the time to a 1930s astrophysicist. So this again would have been done on photographic plates. It was in the 1970s that the CCDs began being used and enabled a much deeper images and also better calibration across the field of view. So that was really key, because that meant that astrophysics could now be a far more exact science. So we could talk about accuracy, precision, and uncertainty in a way that we hadn't done so before, because we were dominated by systematic errors. In the year 2000, we ushered in the beginning of the big data era in astrophysics, with a telescope called the Sloan Digital Sky Survey Telescope. So this is a 2.5 meter telescope at Kitt Peak in the USA. And the sky begins to look something like this. And here's an image you can see of the Sloan Digital Sky Survey Telescope. This telescope also isn't a pointed observatory where you put in a proposal and you say, I would like to look at this thing, and you go and look at it. It's a telescope that just maps slowly across all of the sky that it can see, and produces large amounts of data. So this was really the very start of a data era for astrophysics. So now we regularly use much larger telescopes than this, and they reveal the sky in much greater detail. So this is the sky now as revealed by about an 8 meter telescope. And this is me standing here in front of the 8 meter VLT telescopes. That stands for Very Large Telescopes in Chile. And this image really shows us kind of the richness of the universe that we now observe on a regular basis. So bigger is very definitely better in astrophysics, but large telescopes have particular challenges. So the biggest challenges are our gravity and our atmosphere. So how are new technologies and things helping us to overcome these challenges? Okay, so gravity is a problem for astrophysicists, as basically continuous mirrors of many, many meters start to become very heavy. When they become so heavy, they deform under their own weight, and they require kind of unpractically strong, sturdy structures, and a lot of power to move them. So there are a couple of methods we use to respond to this challenge. The first is the use of sensitive actuators. So these are machines which convert energy into mechanical force. And modern telescopes basically have arrays of actuators, which you can see here in the image, at small intervals attached to the underside of their mirrors. So the actuators themselves have enough force and precision that they can basically deform the mirror in such a way that they keep the mirror within a perfect shape. So this helps to keep large mirrors from deforming under gravity, but it also helps to do another thing, which is to correct for the movement of the wavefront that our atmosphere induces. So there's another thing that we use our actuators for. I'm going to just start the actuator movie. And that's to protect the mirror from ground movement. So I was at one of the VLT telescopes when we experienced a magnitude 7 earthquake. Basically, when that happens in an astronomy facility, everybody just jumps up and hugs a screen and makes sure they don't fall to the ground. But the ground shake was very violent. We had both the waves coming through that you could feel very, very strongly. But the remarkable thing was that due to the system of actuators and a ring of clamps that sits around the edge of the mirrors of these the VLT telescopes, and the VLT telescopes have a 23-ton mirror. It was completely protected, and we were back on sky observing again within 3 hours, which was quite remarkable. This technology enabled us to do this. So another method which enabled us to build very large telescopes is interferometry. And interferometry is essentially splitting a massive telescope up into smaller ones that are linked together. So to gain a very high spatial resolution, you want to have a very large diameter telescope. Large telescopes can see fine details from the diffraction, but when light hits an aperture, when the light hits the aperture, it tends to spread out. The smaller the aperture, the greater the spread. So basically, small apertures cause the more blurriness, and the large apertures allowed greater detail. But to get this detail, we don't actually need a complete telescope. So a telescope with holes in it will still produce some wonderful fine detail, but it won't be as bright. So something we can do is build many smaller telescopes, link them all up as if they were simply parts of one really large telescope. And we can make much, much bigger telescopes this way. The difficulty of doing this then becomes a computational one, and it becomes one of timing. So you have to make sure that all the data from all the different telescopes as it's collected is perfectly in sync. And there was a remarkable recent measurement where they used essentially the full diameter of the Earth as our telescope, because they used radio telescopes spaced throughout the Earth. And they were able to measure the inner edges of black hole for the very first time. And that's what you're seeing in this kind of donut shaped image here. So there are now 2 such measurements. So the one that came out this year was a similar measurement, but it was of the supermassive black hole actually at the middle of our own galaxy. It looks very similar again. The spatial resolution that the telescopes achieved here is essentially equivalent to being able to read words on a coin from London if a friend of yours was holding up the coin in New York. So that's the sort of spatial resolution that this telescope was able to achieve. However, for this telescope, they didn't have a direct data link. So the way this was actually achieved is data was collected at all the telescopes. It was given a timestamp independently at all the telescopes. It was put on disks and they were all flown together to a supercomputer, and then they were analyzed there. So that's okay if you're making just one measurement and then you're stopping your measurement and you can go and analyze your data. It's not okay, as we'll see later on, where we want to do surveys that are continuously generating very large amounts of data. So the second challenge for astrophysicists, is our own atmosphere. So the movement of our atmosphere blurs the light from stars, making them appear to twinkle. But it also prevents harmful radiation from reaching us. So that may not sound like a bad thing. It's wonderful for humans, but it's terrible for astrophysicists. We want to collect all of that radiation. So how do we get around these challenges? So the first method, again, is that we could use those sensitive actuators. This time combine them with real-time laser measurements of the Earth's atmosphere. And that way you can get an idea of how the wavefront is deforming. And then we can deform our own mirror very, very quickly in real time with such precision that you can essentially reverse the blurriness, reverse this twinkling that's occurring because of our atmosphere. So this is called adaptive or active optics. And that's a technology actually that's been used to look inside the human eye in a very fine detail, and to do things like try and identify macular degeneration and try and identify glaucoma. So two remarkable astrophysics discoveries that have been enabled using this technology are proof of the existence of supermassive black holes. So these are regions of space so dense that no light can escape, and the direct imaging of other planets orbiting other stars. So on the left-hand side, what you're seeing here is a video of 16 years of data, which are actually all stars, and they're right at the center of our own galaxy. So the stars you can see are moving around, and actually what they're doing here is they're orbiting an object that we can't see. So their motion allows us to measure the mass of this invisible object. And it turns out that the mass of that invisible object is about 4 million times the mass of our own sun. And this object is the supermassive black hole that sits at the heart of our own galaxy. On the right-hand side, this is a direct image of an extrasolar planet that's orbiting another star. So the bright light, the star is right in the center, but it's been blocked out. So a lot of the light from that star has been blocked out with what we call a coronagraph. And the little dots that you're watching move around are actually planets orbiting their own sun. That's what you're seeing in this image. And with the recently launched James Webb telescope, we'll be able to actually do things such as measure the atmosphere of these distant worlds, not just detect them. And so, of course, key things to look for are water in the atmosphere, carbon dioxide in the atmosphere. We're essentially looking for signatures of life. Okay, so there's another way that we can deal with our own atmosphere, and that is essentially just to leave the Earth. We can use planes, balloons, satellites, all of these things to get ourselves high enough such that the water vapor and atmospheric movement don't affect our astrophysical results. Going far into space would be ideal, but it's very expensive, and when your telescope breaks, you can't fix it. But even aircraft flying right at pretty much at the limit of how high we can fly with these sorts of jumbos can get very good results. So the bottom picture I'm showing here is the Sophia telescope. So this lives aboard a modified 747. It's a very wide and short version of the aircraft. And that's why it looks here like it has a very oversized tail. And you can see that there's a hole that's been cut in the side of it. So that is a 5 meter by 4 meter hole. And there's a 2.5 meter telescope that's mounted there on this airplane. So I was actually lucky enough to fly on board this observatory taking data. It flies much higher than a regular jumbo jet, which flies maybe 28 to 38,000 feet. Sophia operates up at more like 46,000 feet. So at this height, the air density results in less lift being generated for a given airspeed. So the airplane needs to fly faster if it doesn't want to stall. But the airplanes also have a maximum stall speed. So as the air flows over the wing, it's accelerated. The wing's acceleration progresses towards the speed of sound, shocks form, and this reduces the lift. But the speed of sound is going to be decreasing with the cold air at the high altitude. So the higher the plane flies, the closer its high and low speed limits approach one another. So this plane has to be flown. It's flown by NASA test pilots, and it's flown with a very, very high degree of precision, because usually there's about 50 to 100 knots margin of error in the speed, but Sophia pilots only have a few knots to play with between their high and low speed limits. So another thing that the precision flying is needed for is because the main pointing of the telescope is actually done by the plane itself, by the pilots, and very fine adjustments made by the telescope and instrument teams. So steadying a camera on the ground is not a trivial task. If anybody's ever tried to take their picture and ended up with very blurry images from their camera phones and things, you'll know this. So trying to do it kind of bouncing along in turbulent air at more than 13 kilometers high in the sky is quite a feat. And here's a little video of the telescope mounted in the Sophia airplane. So Sophia can actually maintain a pointing accuracy of a half an arc second. So that's better than width of a penny seen from 2.5 miles away. In this video, there are some major movements that are being done by the instrument team, but the bouncing around that you're seeing looks like the telescope's bouncing around inside the plane, but this is actually the telescope being perfectly balanced, and it's the plane bouncing around the telescope. So this is great, and we can make these sorts of observations. However, ultimately, the very best thing, if you want to get rid of all these challenges, is just to go deep into space. So if we're going to go further into space, where would be a good place to go? So we need things that are one, in a stable orbit, two, not too far away, so we can easily communicate with the spacecraft. We want to be able to collect the sun's radiation for power, and we need to shield our sensitive astrophysics sensors from the sun, from the Earth, and from the moon, all of which are very bright. So there are 5 stable points in our Sun-Earth system we could go to, but only one of these essentially satisfies all of those conditions. One of them in particular, which is the condition to shield the instruments, and so that's L2. And this is why we sent the James Webb Space Telescope there. James Webb is up there, and it's unfolded, and it is sending home its first pictures. And I wanted to spend a couple of minutes on that, since it's the flagship telescope that's launched this, that's been sending back its recent images. So it's quite a feat of engineering. James Webb has an extraordinary number of moving parts for a satellite. You would usually do your very, very best to minimize all of these. So every part that moves is a part that can go wrong. But James Webb has a lot of them, and frankly is working well. To achieve the size of the telescope, it's basically folded up and built in segments. And here we see the kind of the unfolding sequence of James Webb. This is one of the first images that it sent back. So the image is sharper and deeper than the Hubble deep field images, and despite only taking a fraction of the time. The 6 bright diffraction spikes that you can see around one of the bright objects here are just due to the hexagonal shapes of the mirrors. And so they're made in segments in order to be able to fit inside the rocket. And JWST has basically already set records for the oldest galaxy as ever to be imaged. So some of the light that you're looking at, even within this particular image, has taken more than 13 billion years to reach us. And we can use the universe actually to do even better. So the universe itself can be used as a giant telescope. Now, mass bends light, so it actually acts like a large glass lens inside of a telescope. And this is what you're seeing happen with these arcs that we've just zoomed into here in this image. So those arcs are actually galaxies that are very, very far away, and they're behind a more massive foreground cluster of galaxies, which is a very massive object. And that massive object is bending the light into these arc-like structures. So much like a regular telescope, this process enables us to use the mass in the universe as basically a giant magnifying glass. We see even further back than our telescopes could have been engineered for when we use this sort of process on top of our telescopes. And you can see all the way back to the very first objects that formed in the universe. So what other astrophysics have we achieved with all these technological developments? So there have been a lot, but a few of what I think are the highlights. So this is the first light ever to have traveled through our universe. This is the cosmic microwave background. They're the first photons which escaped basically the initial soup of plasma that was in very hot early universe. And when things cooled down and they found a way to escape, they found a way to us, and that's the imprint of the cosmic microwave background. Oh, and my light in my office has gone off. It's detected that I'm here. So I might just stand up and wave at my office light, sorry. So the cosmic microwave background was first detected by Bell Labs radio astronomers in the 1960s. This particular image was taken by a satellite, and the most detailed images of the cosmic microwave background we have now are satellite images. And what they are essentially telling us is that our universe is remarkably uniform. There's only small perturbations in temperature, and these gave very strong support for like our currently favored cosmological models. Going above our atmosphere has enabled us to do another thing. We can access all the different parts of the electromagnetic spectrum. And using this, we've managed to uncover the most energetic events in the universe after the Big Bang. And those events are the collisions of galaxy clusters. So galaxy clusters contain thousands of galaxies. And galaxy clusters can collide. And when they do, they release staggering amounts of energy. So in the optical, we don't really see the difference. So what you're seeing here is an optical image, and you can just see lots of galaxies here in this image. You might be able to work out two slightly more dense structures. But in the X-ray, we see the hot gas that's between the galaxies, and that looks here like a bullet. So this is a cluster that was aptly named the bullet cluster. So the hot gas is collisional, and during this interaction in the galaxy clusters, it's been heated by friction, it's been shocked, and it forms this bullet here that you're seeing in pink. The blue color shows where most of the mass is in the system. So the blue color is actually predominantly here tracing a mysterious substance called dark matter within the system. That is the vast majority of the mass in this system. We've been able to also image the most powerful single objects in the universe. So the most powerful single objects are supermassive black holes. They usually lie dormant, but they can be provoked to trigger enormous amounts of energy. And this energy is released as giant jets, and that sends shockwaves and can send shockwaves through an entire galaxy. And there's enough energy that comes out of a single supermassive black hole to be able to unbind all of the gas within its host galaxy. So the image that you're seeing here is a combination of X-ray, radio, and optical images. And we've recently gone beyond the electromagnetic spectrum to detect gravity waves in the universe, generated by the merging of very dense objects like black holes. So these events are so spectacular, they essentially just shake space-time. And they do this so violently that we can actually still detect this shake on Earth. Now, when black holes are coalescing, there's a frequency change that occurs over time. And so that enables us essentially to turn this into a sound, and you can actually hear the sound of black holes colliding. So I'm going to try and play that sound for you now. Hopefully you heard a sort of chirping noise. So that there was the sound of the densest objects in our universe coalescing together. And finally, the big change recently, and the change that's going to, I think, drive the next years, has been changes in computing and computing power. So computing power has enabled discovery in astrophysics. We can make models of the entire universe's evolution. Here's one of those models that I'll play for you in a video. These models can be tested and used to better constrain our universe's geometry and to better constrain our universe's growth. The video that we're playing now is one of those. So you can see that it starts with, it's a hydrodynamical model, and it starts with just where the matter is, and that's in the blue light here. But you can see all these explosions going on, and that's feedback processes with energy being injected back into the surroundings by a supermassive black hole that has started feeding, or by the generation of stars that has turned into supernovae. So these models have enabled us to determine that the majority of stuff in our universe is not the stuff that makes us. We're only about 4% of the universe. The majority is the majority of matter is mysterious dark matter, which appears to only exert gravitational forces, not electromagnetic ones. So it's hard for us to observe. And then there's an even more mysterious dark energy, and that appears to be driving the acceleration of the universe. We have no idea really what these are. And so these are a big focus of the next generation of astrophysics and cosmology experiments. So this is our last 13.9 billion years. The first light which escaped, so we've seen that's the cosmic microwave background. The first stars that formed, we're seeing those now with JWST, with lensing helping us. Those stars then became galaxies. Some of those died. Some of the stars died. They made black holes. Galaxies merged. They become more and more massive. And we essentially end up where we are today. The vast majority of this knowledge, most of what you're seeing in this image, has really only been uncovered in the last 100 years. And it's done so because of the technological advancements during this time period. So where are we going next? So we're launching bigger telescopes into space, not only as satellites around our Earth, but we're going to send them further away to better viewing types. We're building telescopes the size of Big Ben on Earth. The UK is leading the way, leading an enormous array of radio telescopes that will come online in the next few years. Will generate more data in a day than the internet currently does. The data challenges that you can imagine are going to be absolutely huge. And so this is leading to many collaborations with industry who are interested in questions of how you store this data, how you analyze these large data sets. The astrophysical questions we'll be answering are things like, how do supermassive black holes evolve? How do they work? In a couple of years' time, we should probably have our first measurements of, like, detailed measurements of atmospheres of exoplanets, looking for signs of life on other planets. And we'll be pinning down the nature of dark matter and dark energy, which may lead even to things like a revision of how we think fundamental forces operate. So it seems that bigger is better. I've said before, bigger is better in astrophysics. That's certainly the way we're headed, but that's not without a challenge. So this is a telescope that is up and running now. It's called the Dark Energy Spectroscopic Instrument. It takes spectroscopy with these little tiny robots here that twist and turn and find themselves onto a galaxy or a star or whatever you want to look at. There's 5,000 across the field of view. And this takes spectroscopy of about 30 million objects. We have the Gaia satellite, which is doing repeat imaging now and has given us data on 1.8 billion stars and their locations, looking at how they move. Two telescopes that should come online in the next year. So that's the Euclid satellite and the Large Synoptic Survey Telescope, will give repeat imaging of more than 2 billion galaxies. And they'll be generating about 15 terabytes per night of data. These aren't staggering amounts yet. But the next thing is the Square Kilometre Array, this huge radio telescope, radio interferometer. So this is expected to be generating about a petabyte per night per telescope. Of the survey data that needs to be collected and stored for people, it will be about 8.5 exabytes in total. So we obviously have huge challenges coming up. We have challenges of data storage, we have challenges of data processing, and challenges of data analysis. For the SKA, data storage will be done, regional centers are planned, because the amount of data that will be there is more than astrophysicists will be able to store within their home institutions. So they're planning large supercomputers that will be on site and do data processing immediately at the location of the telescopes. So one is in Australia and one's in South Africa. And then after that processing, so much of the data won't be seen, it will have to be thrown away. But after that processing, data will be stored in regional centers throughout the world. In terms of the data analysis, so this is something that we are more familiar with in astrophysics. I said that the Sloan Digital Sky Survey started the big data era, and that's been going for more than 20 years now. So machine learning methods in astrophysics are very common. We do tend to do large statistical studies. We have imaging data, so two-dimensional data. Spectroscopic data is typically one-dimensional, though sometimes we have 3D imaging and spectroscopic data sets. And another very common thing for astrophysics is using time series data. And that is something that's only going to become more and more important, because many of the telescopes we're planning for the future are going to be collecting time series data. So many machine learning methods used throughout astrophysics, and classification and regression is used very regularly. The biggest challenges, of course, always with machine learning is how you train your data in a robust way. So this is done often with mock data sets, but then there's an explicit assumption that you understand the physics, that if you get your physics wrong for your mock, then your inference on your real data will not be what you really want it to be. Or we try and label data sets. So one of the methods that's been very successful is using citizen science to help us label data sets. So this is a slide here that shows the Galaxy Zoo. So you can see the statistics here, 92,000 volunteers, close to 300,000 classifications of galaxies. So lots of people have gone online, have classified galaxies, and using the questions and the framework that the Galaxy Zoo team have set up. So you're asked questions like, is this a red galaxy or is it a blue galaxy? Is it a spiral? Is it smooth? Things like this. And then there's a task to work out who is a reliable trainer of this data set and who is a non-reliable trainer. And the human scores then get weighted. And this all goes into training large neural nets for deep learning, essentially. And it's used to answer questions, to do classification for galaxies in large surveys, and to answer questions like, are supermassive black holes triggered in galaxy mergers, for instance, because you could go and you could say, I would like my neural net to find all merging galaxies. So those are the sorts of questions and ways in which we use machine learning. Now, I said before that Earth was not the very best place for telescopes, and it's not, and it is Red Planet Day, so maybe we should be thinking about other places to put our telescopes. And people are thinking about the moon, and they're thinking about Mars. The moon has had more serious thought, I would say, with lots of people wanting to put particularly radio telescopes on the far side of the moon. That would be wonderful because, of course, it cuts down on the noise from human populations. However, we are also planning to increase radio noise around the moon. So the moon may not be the best option anymore. And perhaps Mars is a better option. But this causes another data challenge for us, and that's one of data transfer. So satellite data, getting satellite data home is not trivial. JWST started with storage on it that was just 150 megabytes in tape storage. And then on the third go, when they updated the Hubble Space Telescope, they put in a solid state drive, which you're actually seeing in this black and white image here. This is what the solid state drive looked like, and that's 1.5 gigabytes. So it doesn't sound like a lot to us. JWST has 68 gigabytes. It will transmit data twice daily, and it will transmit about 28 gigabytes of data in each 4-hour window that it transmits to the deep space network. So this may not sound like a lot of data, but of course, the rates of transferring data back from deep space are very, very slow. So this does take a long time to transfer that amount of data. And JWST is really the first time astrophysicists have had to stop and think when they're designing their own experiments to apply for time on JWST. You often think about lots of instrumental characteristics and things like this, but this is probably the first time you've had to think about your data rates as well, very, very carefully, and really consider, do you want all your data home, or can you make do with parts of data sets and so on, window your data, don't send home the whole image, and things like this. It's a shame to lose data, but this is the challenge that data from space brings. So there have been lots of attempts to make small satellites for astrophysics. This was one of them, the Asteria telescope. It was the first one. And I think it was actually a 12U satellite. There's a few CubeSats that have been launched in the last few years as well. Qt is a 6-unit CubeSat that's going to look at mass loss rates of exoplanet atmospheres. And there are a number of CubeSats for astrophysics that are being developed to go to the moon or to go to other planets. So small satellites are great. We're seeing a small satellite revolution. I actually had a couple of students who are on this this slide spent 4 weeks building the first UOP CanSat with me this summer. But there are problems with small satellites. So there's overcrowding. Of course, more satellites means more data needs to be transferred home, and they're in an extreme low power environment. So the next years, we need to consider also what new methodologies are we going to build to combat this. One of which that I'm thinking about a lot at the moment is onboard processing and onboard machine learning in a very low power environment. Can we get those very large astrophysics deep neural networks that have been trained on supercomputers to actually operate when they need to be powered by a solar panel? So these are the sorts of questions and advances we really need to make, I think, in the next 10 years, 20 years or so. Okay. So what will the next 100 years bring? So we've learned a huge amount in the past 100 years. We've learned it essentially from technology development and a lot of hardware development. I think the next step will need an awful lot of computational tools. And maybe bigger might not always be better. Maybe more efficient might be better. And I think I'll leave it there.
Thank you very much. That was absolutely brilliant. And I'm sure that we're all absolutely delighted with that presentation from Dr. Rebecca Canning from Portsmouth University.